Imagine, just for a second, that you're driving down the highway.
Okay.
You're doing like 70 miles per hour. You can hear the wind whipping past the glass. You can feel that subtle hum of the asphalt right beneath you.
Yeah, standard road trip stuff.
Exactly. And your hands are firmly gripping the steering wheel. But now imagine that the steering wheel in your hands is completely physically disconnected from the front wheels of your car.
Which is a genuinely terrifying thought for a lot of people.
It really is. I mean, no metal shaft, no gears. There is literally no physical link whatsoever keeping your 2-ton vehicle on the road. It's just a computer basically translating your hand movements into digital signals.
Yeah, it goes against, well, over a century of automotive intuition, right? Where we just inherently trust this physical piece of metal to connect our hands to the tires.
It sounds like pure science fiction, or
Right.
honestly, like a total recipe for disaster. But welcome to today's deep dive, because today we are actually exploring this monumental shift in automotive history.
The end of the mechanical steering column.
Exactly. And engineers are proving this isn't just theoretical anymore. To help you navigate all this, we're unpacking a really fascinating stack of sources today. We've got a pretty dense, incredibly detailed engineering study from the International Journal of Advanced Research, Ideas, and Innovations in Technology.
Right, specifically analyzing autonomous vehicle mechanics.
Yeah. Plus, we're weaving in some official April 2026 press releases from Mercedes-Benz, who are actively rolling this tech out. And just to make sure we aren't only talking about abstract math here, we have hands-on test drive reports from Edmunds and some Italian automotive journalists who actually took these prototypes out on the open road.
So our goal today is to really figure out the mechanics of how this technology, which is known as steer-by-wire, or SBW, how it actually functions under the hood.
Right.
We're going to uncover why engineers consider it like the missing link for true self-driving cars. And we'll explore what it actually feels like to pilot a luxury vehicle with what is essentially a giant, highly sophisticated video game controller.
Yeah, a video game controller for a 2-ton car. It's wild. But to really grasp how radical a departure this is, I think we first have to look back at how long we've been physically chained to our front wheels.
Oh, absolutely.
Because the concept of a round steering wheel is so universally ingrained in us, we kind of forget that it had to be invented in the first place. I mean, the very first automobiles, like the 1886 Carl Benz patent motor wagon, didn't even have a wheel.
No, it used a simple crank, sort of like a handle you'd use to wind up a music box.
Exactly.
Because people were just transitioning from horse-drawn carriages. So the mental model was pulling reins, right? Not, rotating a flat disc. That physical circular connection wasn't even introduced until 1894, during a historic drive from Paris to Rouen on a Panhard and Levasseur vehicle.
Wow, 1894.
Yeah, and then if you fast forward to 1958, you get the Adenauer Mercedes, which introduced power steering that used hydraulic fluid to just make turning that physical wheel easier, so you didn't have to muscle the car around a parking lot.
Right, but the fundamental architecture underneath it never actually changed. I mean, even the modern electric power steering like the car you probably drove today, it still relies on a physical metal column spinning a gear, the pinion.
Yep.
And that gear sits on a toothed metal bar, the rack. You turn the wheel, the gear spins, the bar slides left or right, and physically pushes the front wheel side to side. Modern systems basically just slap a helper electric motor onto that same metal skeleton to give you a boost.
Exactly. It remains this very rigid mechanical chain of command, which is why steer-by-wire is such a massive leap. The engineering study we're looking at breaks down how the new system completely severs that chain.
Okay, so how does it actually work?
Well, the architecture is split into two completely isolated halves. Upstairs in the cabin, you have what they call the input subsystem.
Right, the steering wheel.
The steering wheel plus sensors to detect the angle and force of your turn, and a feedback motor. And then downstairs, sitting right on the axle, is the actuator subsystem. That's an electric motor bolted directly to the rack and pinion, alongside its own wheel angle sensors. And the only thing connecting upstairs and downstairs is wires.
Okay, let's unpack this with an analogy, because I think visualizing the mechanics here is super crucial. So traditional steering is basically like a mechanical typewriter.
Oh, like that?
Yeah, like your finger physically strikes a key, which swings a metal arm, which physically smacks the ink ribbon onto the paper. It's a direct mechanical action. Your physical force creates the direct outcome.
Right.
But steer-by-wire is, it's a digital keyboard.
That's exactly it. Because with a digital keyboard, you press a key and a processor just registers the input. The computer then have to decide to render that specific letter on the screen. There's literally no mechanical link between your finger
Yeah.
and the pixel on the monitor.
Yeah.
And just like a digital keyboard, you can program what the keys do. Pressing A doesn't always have to output an A if the software says otherwise.
That is such a huge shift. The relationship between input and output becomes entirely flexible. But wait, the feedback motor upstairs seems like the real magic trick here.
Oh, absolutely.
Because if you don't have a physical connection to the road, the steering wheel would just spin freely, right? Like an unplugged arcade cabinet.
Exactly. It would just feel completely dead. So the motor up in the cabin has to artificially create resistance. It basically tricks your brain into feeling like you're actually pushing heavy rubber tires against asphalt.
It's a massive illusion.
It is. And it's all orchestrated by this electronic controller sitting between the two halves. That controller is the brain. It reads what your hands are doing upstairs, calculates all the physics, and fires the signal down to the motor at the wheels, telling it exactly how far to push.
Okay, which obviously brings up the biggest question for me. We've spent, 130 years perfecting this mechanical typewriter system. It works basically flawlessly. Why on earth are we throwing away a century of mechanical reliability to stick a computer in the middle?
Well, because that mechanical reliability is actually the biggest bottleneck for the whole future of self-driving cars.
Really?
Yeah. The core issue, which is really highlighted in those engineering sources, is inertia. When an autonomous computer wants to steer a traditional car, it has to fight the physical reality of the cabin.
Okay, let's try to visualize that. So, say an autonomous driving computer spots a child running into the street, right? And it needs to make a split-second evasive swerve.
Right.
The computer's electric motor isn't just turning the tires. It actually has to physically backdrive the entire heavy metal steering column and violently spin the actual steering wheel inside the cabin backward.
Yes. It's kind of like trying to move a large, heavy marionette puppet, but you also have to forcefully move the thick wooden control sticks and the heavy arms of the puppeteer holding them.
Oh, wow.
You're fighting this massive physical resistance. The hardware itself is just sluggish, even if the software brain is light and fast.
So, by severing the mechanical link, the motor down at the wheels only has to move the wheels. It doesn't have to backdrive all that heavy metal into your lap.
Exactly. It takes far less energy, and it executes the turn exponentially faster. And once you digitize the steering and get rid of that mechanical baggage, you can let artificial intelligence completely manage the messiness of the real world.
Okay, so the paper gets into this, right?
It does. The academic paper goes really deep into the specific controllers that make this possible. One of the primary algorithms is called NAST-SM.
NAST-SM.
Right. It stands for Nested Adaptive Super Twisting Sliding Mode.
Okay, that is a very heavy engineering acronym.
It is a mouthful. But the problem it solves is actually fascinating. It acts basically like noise cancellation for steering physics.
Noise cancellation, like headphones.
Yeah, exactly. Imagine an autonomous car driving over a heavily rutted washboard dirt road. The front wheels are bouncing and vibrating and twisting violently, right?
Right, yeah.
In a standard car, all that violence travels straight up the metal column and shakes your hands. But if an autonomous computer is trying to read the angle of those front wheels to keep the car straight, that bouncing dirt road creates a storm of chaotic data.
Oh, I see. So the computer might misinterpret a harsh vibration from a pothole as like a command to turn.
Exactly. So the NASM controller prevents this by using a fuzzy neural network. Instead of just looking at the raw movement of the wheels, the AI analyzes the frequency and the duration of the vibrations in real time.
So it's looking for patterns. If it sees a sudden, really high-frequency jolt, the neural network identifies it as a pothole and just completely filters it out. The computer ignores it.
Right. But if it sees a smooth, sustained, low-frequency movement, it recognizes that as a legitimate steering input or, a sweeping curve in the road. It basically scrubs the data clean before the car can overcorrect and crash.
That is so cool.
And then you have the second algorithm they talk about, which is VHRMPC, or Variable Horizon Robust Model Predictive Control. This is the predictive brain. It utilizes something called residual dynamics.
Okay, you've got to break that down for us because residual dynamics sounds like something straight out of a theoretical physics textbook. How does that actually steer a car?
Basically, it calculates the difference between a prediction and reality.
Okay.
As the car enters a turn, The AI's mathematical model predicts exactly where the car should be in the next few milliseconds, based on the steering angle and the speed. But obviously, the real world is unpredictable.
Right, like maybe there's a patch of wet leaves on the road and the car slips like a fraction of an inch outward.
Exactly. So the actual path deviates from the predicted path. That difference is a residual error. The AI calculates that residual error instantaneously and applies microscopic corrections to the wheel angle down at the road level.
Wow.
Yeah, it stabilizes the turn before the car even has a chance to fully break traction.
What's really wild to me about all of this is what it means for the actual person sitting in the driver's seat. Because the system is completely digital, the machine learning aspect means the car can learn your specific personal preferred steering effort.
Yes.
Like if you love a heavy, sporty, resistant feel to your steering wheel, the AI just learns that profile. It commands the feedback motor in the steering wheel to simulate that heavy tension for you. It literally custom tailors the physics to your taste.
It really does. And crucially, it also solves a major safety flaw in current self-driving systems. It completely separates your input from the computer's output.
Oh, right.
Because think about a traditional car with lane assist. If the computer suddenly swerves to avoid a crash, the physical steering wheel in your hands violently spins, and a panicked driver will often instinctively grab the wheel to stop it from spinning out of control.
Which physically blocks the computer from finishing the turn.
Yeah.
You're overriding the emergency maneuver.
Exactly. But with steer-by-wire, the computer can crank the wheels downstairs to dodge a collision without moving the steering wheel upstairs at all. The driver's panic grip can't physically block the car from saving their life.
Man, the engineering is brilliant. But cars aren't just math equations solved on a chalkboard, right? They're visceral, physical machines. They are meant to be driven by human beings with very specific expectations.
Definitely.
So if the computer is doing all this predictive noise canceling stuff in the background, what does it actually feel like for the human whose hands are on the wheel? Which brings us to the hands-on test drives.
Yes. Fun part.
Right. Journalists recently went out to Faro, Portugal, to get behind the wheel of the 2027 Mercedes EQS prototypes.
And it's funny because the very first thing they noted had absolutely nothing to do with the software. It was actually the physical design of the cabin.
Right, because Mercedes completely replaced the traditional round steering wheel with a flat yoke. It looks almost identical to the close you'd find in an airplane cockpit.
Yeah, just a rectangle, basically.
And the Edmunds reviewer pointed out a massive practical benefit to this. In a standard luxury car, the top curve of a round steering wheel frequently blocks your view of the driver's display screens, or even the road directly over the dash. Chopping off the top half of the wheel to create the yoke fixes that visibility issue instantly.
It really opens up the cabin.
But the most jarring part of the test drive was taking a U-turn.
Oh, yeah. Think about the physical mechanics of a U-turn in your car right now. You are doing these crazy hand-over-hand maneuvers, shuffling your grip, spinning the wheel 2 or 3 full rotations just to get the tires to lock.
Yeah, it's a whole upper body workout. But with the steer-by-wire yoke, you never actually move your hands. You keep your hands locked at 9 and 3. You just rotate the yoke about 120 degrees to the left. Like, you don't even cross your arms.
Wow.
Because the system is digital, it dynamically changes the steering ratio based on your speed. So at, say, 5 miles an hour, the software knows a 120-degree tilt means you want a full U-turn. The electric motors down at the wheels instantly crank the tires to maximum lock. The Italian automotive engineer who was riding shotgun brilliantly called it a lazier way to drive.
Which is so true. And in the context of a luxury vehicle, requiring far less physical exertion to manipulate this heavy machine is basically the ultimate praise. You simply point the yoke and the car does the heavy lifting.
Okay, wait, hold on. I have to push back on this a little bit.
Go for it.
We're talking about a purely digital signal connecting my hands to the wheels. My wireless headphones stutter when I walk into the next room. My home Wi-Fi lags constantly. If I'm doing 70 on a mountain curve, isn't a digital lag going to put me in a ditch, like a bad internet connection?
It's completely understandable to think that. It's the most common intuitive fear people have about this tech. But the data from the test drives shows it is actually a myth, mostly based on a misunderstanding of how mechanical systems even work.
Really? A myth?
Yeah. The Italian review specifically tested for latency. They aggressively jerked the yoke back and forth to see if they could catch the computer lagging, And they found that the steer-by-wire system actually has less latency than a traditional steering column.
How does that even make sense? A direct metal rod has to be faster than a processor calculating an algorithm, right?
Well, it would be if it were just a single, solid steel rod. But a steering column is a really complex assembly. It has U-joints to change angles around the engine block. It has rubber bushings designed to absorb engine vibration.
Oh, right.
When you turn a physical wheel, you are twisting all of those components. You have to literally compress the rubber and take up all the microscopic slack in the metal joints before the tires even begin to receive the force of your turn. There's a real, measurable physical delay as the mechanical energy travels down that column.
Oh, I see. The metal basically acts like a very stiff spring winding up.
Exactly. But with steer-by-wire, the signal travels from the sensor to the actuator via electrical current. The processor calculates the NAST, SM, and VHR-MPC algorithms in roughly 1 millisecond.
1 millisecond.
Yeah. The Italian journalist noted the response is so instantaneously fast, the front end of the car actually feels wildly aggressive at first. He described the car as feeling like it wants to, quote, bite the apex of the curve before your brain has even finished processing the physical movement of your hands.
Okay, so the lag is a total myth. But, the system isn't without its flaws. To keep things balanced here, we have to talk about the uncanny valley of the steering feel.
Ah, yes, the simulated road feedback.
Exactly. The Edmunds journalist pointed out that while Mercedes has built the best steer-by-wire system they've tested, they specifically noted it feels much more natural than the system in the Tesla Cybertruck. The simulated feedback over bumps still feels a bit artificial.
Yeah, that makes sense.
Because the physical road isn't pushing back on your hands anymore, right? An electric motor in the steering column is analyzing a bump and deciding to vibrate your hands to simulate what it thinks a bump should feel like. It's a digital facsimile of reality, and the human brain is highly sensitive. It knows when it's feeling a recording instead of the real thing.
Right. Engineers are basically trying to digitally recreate a purely analog sensation, which is incredibly difficult. But, this reliance on electronic simulation and digital signals raises a far more terrifying question for the average driver.
The ultimate nightmare scenario. What happens if the power dies while you're driving? You turn the digital yoke, the computer is dead, and the car just keeps going straight into a wall.
It is the very first scenario any automotive engineer attempts to solve when designing this. The academic paper and the Mercedes press materials outline a seriously rigorous, almost paranoid level of redundancy.
I would hope so.
Oh, yeah. Mercedes has run over 1 million test kilometers on test benches and then another million in real-world traffic just to prove the fail-safes. The system features dual signal paths, redundant sensors, and 2 completely separate power supplies.
Okay.
If one entire half of the computer system shorts out, the shadow system takes over instantaneously without the driver ever even noticing.
But the engineering paper highlights an even more extreme failsafe, right? Because what if the steering actuator itself, the actual physical motor down at the wheels, completely seizes up? Like the data signal might be perfectly fine, but the wheels physically cannot be pivoted. How do you steer?
Yeah, the paper details this amazing backup system called steer-by-brake, utilizing technology from suppliers like Nexteer. If the front steering motor dies, the car communicates with the electronic stability program and actually uses the brake calipers to turn the vehicle.
This blew my mind. It's exactly like being in a canoe. Like, if you want to turn left in a canoe, you drag your oar hard in the water on the left side right. The drag slows down that side of the boat, which physically pulls the nose left. The car does the exact same thing. It selectively clamps down heavy braking force on the left wheels while letting the right wheels roll freely.
Exactly. The friction physically yanks the nose of the car in the desired direction. Furthermore, Mercedes pairs this with their rear axle steering. The rear wheels on the EQS can pivot up to 10 degrees independently.
Oh, wow.
So even with a catastrophic failure of the front steering motor, the car uses the brakes and the rear wheels to safely navigate the car over to the shoulder.
It is just an incredible feat of engineering to make severing the column safe. And what's truly fascinating to me is how removing this one single mechanical link sends this massive ripple effect through the entire architecture of the cabin.
Oh, completely.
Because the steering wheel is now a flat yoke and it no longer needs a top rim to connect to a central column, the interior designers basically had to throw out the rulebook.
Yeah, the physical layout of the safety equipment had to be entirely re-engineered.
Think about the driver's side airbag. Normally, an airbag deploys out of the center hub and uses the rigid circular rim of the steering wheel as a structural backing, right? It literally presses against the top of the wheel to stay upright.
Right.
Mercedes literally had to invent a completely new internal support and folding architecture for the airbag. Without that top rim on the yoke, a traditional airbag would just flop over. So they engineered a new internal skeleton so the airbag deploys and actually holds its rigid shape suspended in midair to catch the driver perfectly.
It's just a perfect example of how interconnected vehicle design really is.
Yeah.
A change at the axle requires a fundamental change in the fabric of the airbag. But if we pull back to look at the larger industry trend, all of this, the yoke, the expanded cabin space, the digital control algorithms, it's all laying the foundation for the ultimate luxury in transportation.
SAE Level 3 autonomous driving.
Precisely. We are entering an era where the driver is legally permitted to take their hands off the wheel and their eyes off the road in certain conditions. Mercedes' Drive Pilot system is already clearing regulatory hurdles for this right now. And when the car is driving itself, a massive fixed steering column jutting right into your chest is just an obstacle.
Right. Without that mechanical column, you can just push the flat yoke away into the dash. The driver's seat transforms. You can literally sit back, recline, and stream a movie on the hyperscreen while the car manages stop-and-go highway traffic. The cabin stops being a functional cockpit and fundamentally transforms into a mobile lounge.
And that is the true mission of steer-by-wire. The easier U-turns and the filtered road noise, those are wonderful side effects. But the primary goal is really bridging the gap between the manually driven cars we own today and the autonomous lounges we will inhabit tomorrow.
So, to kind of bring all these threads together for you, after more than a century of physical connection, the steering wheel has finally been untethered from the road. The transition from physical mechanics to a purely digital interface, from the heavy typewriter to the customizable digital keyboard, is making cars lighter and infinitely faster to respond. By eliminating the heavy inertia of metal gears, we're allowing AI algorithms like NASDSBEM to filter out chaotic road noise and predictive models to steer the car with millimeter precision.
Yeah, it replaces mechanical limitation with digital adaptability. And it utilizes massive redundancies and ingenious fail-safes, like steer-by-brake, to make sure it's safe.
It's the necessary evolution to prepare our vehicles for an autonomous future. And we want to explicitly thank you for joining this deep dive today. We know there is endless content out there, and we truly appreciate you spending your time with us to learn something new and trusting us to help navigate the complex, rapidly changing engineering of the automotive world.
It's a fascinating technological journey, and honestly, we're really glad you're on it with us.
We want to leave you with a final, lingering question to ponder on your own. We talked about how the feedback motors in the yoke use digital signals to simulate the feeling of the road. Well, if a car's computer becomes perfectly capable of simulating the exact resistance, the subtle vibrations, and the perfect, authentic feel of a winding mountain road through electric motors, are we still actually driving? Or are we just passengers operating a hyper-realistic driving simulator that happens to be moving through the real world?